Now we're recording. So we're going to go over intakes today. We'll look at a few of my favorite intakes and just throughout the history of FRC and why they're good. Okay, Marcus is here. Okay. Hi, Marcus. Okay. So let's just look at some different intake design concepts. I don't know if we'll have enough time to design a whole intake today because they are pretty extensive, but I'll try and start one and see if we can go with it. So basically what an intake is it brings something from the outside of the robot into the robot. It takes it in, and it needs to work with different constraints depending on the game. So either the size of the game piece, the location where the game piece is coming from, and a lot of times where it needs to put it. So a good intake is simple and doesn't require a lot of setup on the field. By that I mean you can pretty much just roll up to it and then you have it. So on the next slide, yeah. So 99% of the time, the most effective intake is going to be some type of roller. And so if you look at like, I don't know if you guys have watched like world championship stuff, but yes, Caleb, touch it, own it. It's my favorite thing. If you watch Einstein matches, like pretty much every single robot on there is going to have a roller intake of some kind. I think the exception is last year for Deep Space 971 had like a suction intake that was super cool that went through like 30 something I'm forgetting the word, but like a lot of different changes throughout the design, and they worked really hard on it and it worked pretty well by the end, but even that wasn't even the most effective intake and they didn't make it to the finals. So yeah, pretty much what you want is for the robot to do as little as possible to get the game piece, and we use this phrase in a lot of different situations. You'll hear it if you watch other presentations, but it's like touch it, own it. So if you look at this robot, this is 254's robot from 2017. They had these rollers to get the wiffle balls off of the ground. And so pretty much it would just be spinning, and then you would just touch it and it would just be inside the robot. Just pops them right in. You don't have to align it. You don't have to, you know, move around with really uh, difficult maneuvers with the driver. You just roll up to it and they're inside the robot, and it's simple and effective. This isn't too complicated of an intake. It's just two rollers driven by two 775 motors, but it was effective, and I think they won that year, which is confusing because they went to Detroit that year instead of Houston, which they don't usually do. But because there were other teams, I think they won. I might be wrong though. This robot right here is one of my favorites. Uppercut from this is 148's robot from 2018. It was a little bit more complicated because the cube that they used had two different side lengths, so they were able to kind of flip the cube into the right position so that they can intake it. But the overall mechanism is pretty simple. So it was pretty much just wheels, and they just drive up to the cube, and it's in the robot, and then it's attached right to their elevator, and then they can go. And I know you guys aren't really familiar with these games, but we'll watch a few clips, and I'll kind of show you how it worked out. Okay, so knowing what you know is that rollers are really effective, and you want the robot to do as little as possible to get a game piece. What do you think would be a really effective type of intake for like these? If you've ever been in like a pool, these are like it's about that size, like those floaty tubes, or like the lazy river thing, the kind of thing that you sit in. What do you think would be a good intake for that? Or just like a general idea? Rollers? Yeah. absolutely. They do squish a little bit, and we'll talk about how they how compression factors into our design, I guess, a little later. So yeah, you would want some rollers. I animated that in. I figured out how to do that in Google Slides. So this is 254's robot from 2011. Logomotion was the name of the game. And this won the World Championship. You can't really see it that well, but these are pretty much rollers. And this is just a moving arm and an elevator. And it would just pick it up off the ground and then pop it onto one of these guys. Actually, I don't even know if this is the same game, but they're similar game pieces. This might be something different, but the same concept pretty much. And now we are going to look at some cool intakes that I like. So we have the Robonauts from 2017, that's Team 118, Upper Creek Robotics from 2020, and then Madtown Robotics from 2019. And this one should have won Worlds. They got some sort of disqualification. This one did win Worlds. This one, well, 2020 is a whole different mess, but yeah. Yeah. Okay, so let's look at some of these videos. I'm going to turn this down just a wee bit. You don't have to watch the whole video. So here's the first thing I want to point out. This this gear intake is actually not what our design strategy would say to do. This is not a roller. This is a little bit complicated. So probably not the most effective thing to do. It works for them because they're a really good team and they have a lot of time for designing and stuff, but it's not simple. It's not really touch it, own it. You kind of have to mess around with it a little bit, but that's the 2016 robot. Yeah. So their rollers are pretty neat. So they pretty much just have it go right in and it just works well. And okay, the other thing I want to show you is that another part of the game was getting the balls. Okay, here's another thing to watch. Yeah, so you see how back here they were just able to kind of roll through the robot, through the like kind of pile of balls and just intake all of them. And I want to see if they have a clip of them, but the balls would fall out of like the side of the field and they have this open case right here to just let the balls fall in, which is actually the most simple intake, is just doing nothing and rolling up to it, which, you know, would be ideal in all situations. And then here, and you can see the balls just kind of fall into the intake. All right, so what we learned from that is that really effective intake is to either do nothing. So if there's a situation like this year, the balls for creating the name, this year's game, what was it called? I forgot. But the dodgeballs would fall out of this thing, and infinite recharge. Yes, that's what it was called. So pretty much, they would kind of fall out of a thing similar to this, but there would be a person who would roll them out. And what our robot did was just take them in off the ground. It was pretty good at taking them in off the ground, but an even more effective robot at doing that, or an even more effective way to do that, was to just let the ball roll into the robot. So actually, I'll show you that with the 1619 robot here. I already have it paused at a specific spot. So this was their intake. So what our robot did was center the ball with some mechanism wheels, and it would kind of try and get it into our little bumper hole. And this robot went for the even simpler approach of just getting it over, and they had a spinny, a spindexer, I think is what we call it. And so it didn't really matter where it was intaking it. So it would just kind of all sort itself out, which makes for the simplest intake. And you can kind of just go over. I want to see if they, yeah, here, you see they're just rolling the balls into the robot. Yeah. So if you look at a lot of the robots from this year, they pretty much all read exactly the same as this one, for the most part. So that's kind of what we call like a meta robot, where all of the really good teams have pretty much the same ideas, or by the end of the season, they'll have essentially the same robot, because they see what works and they iterate. Iterate is the word I was thinking of before. They iterate their mechanisms to work with, to be pretty much the best that they can, and then they're better. So if you look at a bunch of robots, I think like 254s was like this, 1678 was like this. A whole bunch of robots pretty much had, they were the short ones, they went under the trench, they had the over the bumper intake, spindexer, and the turreted shooter, and some sort of climb. The climb is where they got fancy, but essentially that's what they always did. And you can look at a bunch of these clips because they were able to do it pretty efficiently. They were a solid team. All right. So what we learned from that is that pretty much the most effective intake doesn't require a lot of time, right? Because remember, they were able to take in multiple balls at the same time. They didn't have to, line them up. They didn't have to really do much. They kind of just drove up to it, spun their things, and they just popped into their robot. So I would even say that our intake from last year wasn't even that bad. It was a solid robot that would have done very well if we had the chance to play. Rest in peace. But that one was just faster. It just worked. And there's good intakes, and then there's championship intakes. And the championship intakes require as little, setup as possible. They didn't need to do much on the field, and they just kind of drove up, grabbed it, they're good. Okay, the next one we're gonna look at is Madtown from 2019. For this video, we can look at both of them, because there were 2 game pieces this year. There were these orange balls, and then there were the yellow hatch panels. So their hatch panel mechanism, which was, it was originally their idea. And then if you look at the championship that year, I think pretty much every team in the Einstein finals had this exact intake here. We'll see it better later. But yeah, if you see this intake right here, it's really solid. And they also have this swerve drive, which is really neat, but we don't usually do stuff like that. Yeah, so you see that one, it just drops the ball in. You see this ball isn't centered on the thing, but when it goes in, it just pops it into the right place. And then you can look at this intake. We actually copied this in the off season. Just goes up, grabs it, pops it on. Oh, well, that's a bad example, but yeah. So that was a pretty solid intake. And remember, when you look at this, when you look at the hatch panel, your first thought usually isn't going to be like rollers, because a lot of people didn't do rollers. They did some sort of like piston hook thing. We did like a Velcro thing that didn't work too great, but you know, we tried. But the roller ended up being the meta, as it usually is, because they pretty much were able to just touch it and own it. They would just drive up and they could pop their rollers in and they had it. They didn't even need to be that accurate because it would kind of suck the thing on. So, is there anything else I have? All right. So now I said we could try our own intake. It is 6:23, so we can get through a little bit of it. Okay. So during the season, when we do these designs, there's going to be a lot of prototyping, which is pretty much what we do for the first week of build season. Is we make all of these kind of like, they're not fully fleshed out designs, but we just try a bunch of different things to see what works, and then we get it done quickly and easily, so that we don't have to like, what am I trying to say? So we don't end up fully fleshing out a design that just doesn't end up working, because we want to make all of our mistakes early, and we want to make a lot of mistakes quickly, so that we know what does and doesn't work, so we can put all of our time into a design that's going to be good. So obviously we can't prototype right now. I was planning on having like I tried doing a prototyping experience last year with the design team that sort of worked, but not really. But I was gonna kind of show the game piece and see like, hey, this is what we're gonna try and see like what works with this, and then we can go cat our thing. But for now, I'll just sort of tell you. So this is like, if you guys ever put like Foursquare, it's like that kind of ball. I think it was 13 inches or something when it was fully inflated, but it could like expand or be smaller or something. But pretty much we're gonna want like not too much compression on this, because it doesn't go too much down, but just a little bit, enough so it doesn't slip out. And we want rollers, obviously. So what we can do is start a design. There we go. And let's call this 2019 practice intake 2020. That's confusing. I'll call it practice intake. Actually, first of all, I want to put this in the training folder. I'll call this. What's the date today? 12/5. Okay. Okay, so pretty much what we're gonna want is some sort of roller. And I'm just, I know that this was also a game piece along with the hatch panel, but we're just gonna pretend like the hatch panel doesn't exist, because that whole mechanism of like the flipping in and out of the of these balls was kind of more complex. So we're just gonna work on a really basic roller intake mechanism that's just gonna suck in this ball off the ground and then hold on to it. And then we could like attach it to an elevator or something, but that's gonna take longer to do. So pretty much what we can do is start a sketch. If you guys want to follow along with this, that'll probably be helpful for you guys. But I'm gonna be kind of riffing because I didn't really like fully plan this out. I'm just gonna be going until 7, I guess. So first we'll make the ball. So this is just a construction line because we're just gonna be basing our design around it, and we don't really need it to be too, what am I saying? it's just there for design purposes. I think it was 13 inches. I might be wrong, but we'll just go with that for now in diameter. And then what we can do is start basing our design around it. So we want, let's say we want 2 rollers on the top and bottom. Oh, okay. One design technique we can do is search for 254 design, pretty much. Just look at the 254 2019 and then go into Google Images. And this is pretty much 99% of our design process. So let's see here, they have this one, or yeah. So they had something like this, where it was kind of like 2 wheels on either side plus this top roller. And I think we can just do something like this top roller and the bottom roller also. So these rollers, you can get them on West Coast products. It's a pretty standard part that we use a lot. Okay, so need to remember how wide it is. I'll go with like a 1/2 inch for now, but I don't really remember. Okay, so this is going to be the first roller. We'll call it, oh, that's 2.75 inches. Maybe. Actually, I'll just go into West Coast products. And then we can check it out. It's going to be in this area. Those. And we're looking for these. So this is just a metal tube, and then you put the like the rubber stuff around it. So 1 1/4. I was a bit off. 1 1/4 outer diameter, which is what you're looking for. I'm going to close this tab. Okay. So 1.25 plus there's like I want to say an 1/8 inch of outer diameter stuff. This is an offset, by the way, if you guys don't know that, or 1/4 inch maybe of rubber around it. So yeah, if you want to do what I just did, you press O for offset, and then you click this, and then you want it to be facing outwards, and it pretty much just makes the same thing. And you just set the distance outside. Okay, now what we want to do is determine the spots where we want this to go. So ideally, it would grab it a little past the middle point so that it would be able to jump in without like having too much trouble, or it would be able to grab it without having it like fall out too much. So what we can do is then make a mirror line across, and then we'll dimension this to be maybe like 2 inches past the middle point, and then we can mirror these 2 parts here, and okay, solid. And then we'll have our plates following the rest of the curve. So, I just got a Discord notification. That was distracting. Oh. Okay. Cool. Now we can kind of design the plates around it and see how it would fit together. And okay, but first we need to find the distance between these 2 parts. So we said we wanted a little bit of compression on it, and it's already going to provide that compression just by being not bigger than the like maximum width of this ball. So I think even we can just make these, that doesn't work. We can just make these curves touch. for whatever reason, the coincide function doesn't work with that. So you have to use the tangent. That's fine. So now we can start designing our plates to put around this. So remember, these are going to be on the outside, so the plates can be a little bit wider than the rollers. So we can offset this again, 0.25 inches, and then make some curves coming off of it to a tangent arc. See if that works. No. We'll have to manually do it. Okay. We'll do it like we want this to go like right here, and then be just a wee bit wider. Maybe that wasn't the best spot to put it at. Maybe it was. Okay. Then we can make these tangent, and then all right. Bye, Caleb. Thanks for coming. And then we'll set some distance between these. We want this to be a little. Yeah, but if you guys can kind of see what's like going on, you'll get it. I'll put actually a line going through the center here. We'll just call these coincide, and it's defined not code. Okay, then I'll make another arc going off of it. We'll separate these a little more. We want these two to be horizontal, that's right. And that's doing some wacky stuff. Okay, so these curves really don't matter too much, but because these are going to be on the outside, they're pretty much just holding it. So I can even put this like here or something. But you guys kind of see how this is all fitting together. It's working pretty nicely. I'm actually going to make this construction, these inside parts, because we're not going to CAD them. What we do want to CAD is the bearing hole here, which is going to be 1.25. Yes, yeah, that's how wide it is. Plus the doesn't like it when I put the dimension, even though it puts the dimension in there. And we can mirror that onto the other side. Solid. Okay. And these points right here are the center points for the line, which are going to want to be on the thing. I can even call this one. I'll make these perpendicular. So this can't. Yeah. There we go. Nope. What? Okay. Cool. And if this ball is 13 inches, then the point from here to here is 6.5. So we'll just call the point from here to here 6.5. This is less of an exact science for the CAD, but you can kind of do what you want with it. Okay, well, I don't just put that there. All right, now I want to mirror all of this onto the other side, like that, including this part. And that makes a closed piece. And trying to find what could be a problem with that. Nope. Actually, maybe I'd want to back these up a little bit. I'll delete this coinciding constraint. Back that up a little bit. I'll give it like a ½ inch like space, just where the ball has a little extra room to kind of fit in there. Okay. Next thing we're going to want to do is attach our motors to rotate these. So, actually, let's make this a learning moment. What motors should we use for this? If this is just going to be like a low speed, low torque, or actually maybe even a little bit like a mid-speed, low torque intake. What kind of motor are you going to want in this area? If you guys are familiar with the motors, actually, I'm not sure if you are yet, but yeah, gosh, we probably haven't gone over it enough yet. So probably what we can use here is a 775. I think even like 254 use 775s, or maybe they used Neos on this one, but actually I can't see. Yeah, no, they were going in on those Neos that year, which is pretty cool. But yeah, we can use the 775 here. Go on to West Coast. Actually, no, I want to go on to Vex Pro. Motion. Shapes, 775 Pro. And what we want from here is the dimensions. So we're going to go into a drawing and check it out. And I think we did this last time, but right, we looked up how to make like a motor plate, right? I think so. Okay. So we can maybe just find the bolt circle on here, and then we can cat it in. So this is going to be 2 times an M4 hole. $29. Okay. So we can just put this wherever right now, but we're going to want it to be more so like defined later on. 29 millimeters, is that right? Okay. And then we're going to want our holes right on the edge here. Put a line through it. Mirror this hole over. Right, so this is our 775 mount. I won't put it in the center right now because we don't exactly know where we want it, but you can put it somewhere along this line if you want it. This will pretty much be, we'll put the motor on the outside, most likely, or we can even put it up here, just a little bit above the ball, so it doesn't input on the inside and have the belting on the outside. Yeah. And then this hole right, this hole is 689 plus or minus. All right. this is going to be like the hole for the little stud in the motor that's going to go in. Oh, does that seem right? No. Oh, yes, it does, because that's the bolt circle, not the motor circle. But we do want the motor circle also, the motor dimension, because that's going to be important. So the total diameter of this is where? Okay, this one, 1.665. And this is just going to be a construction line. And we can kind of see how it's going to fit in the area. Does that all make sense how this works? Like, this is the outside motor, these are the mounting holes, and this is the these need to be defined. They're M4 bolts, which is metric type 4, so like 4 millimeters diameter. And you can just do that if you want. Like, if you just type in millimeters, then it automatically converts the units for you and on shape. Pretty sweet. Okay. So now we want a bit of a reduction. So a lot of times in FRC, we're pretty loose about this. We just kind of go like off of like what we think is probably going to be about right. So we don't want a motor like directly driving it, of course. So we'll have some sort of like a belt shakedown, and we want to use a belt in this situation because it's lower torque and a little bit higher speed, and yeah, right? No, lower torque and like lower-ish speed. I know I like kind of defined it pretty solidly here, but it's a lot more fluid than you think, I guess. But yeah, we typically use belts for these kind of intakes because they're not too fast. They're also pretty low torque. And when I say low, it's obviously like relative, because like maybe it's not as low as you would think. But okay, anyway, we can look at the graph for the motor. I'm gonna find that so I can show you what that looks like. Or I guess not. Yeah. So the free speed is about 18,000 RPM, which is like stupidly fast, and that's way too fast for intake. We're going to shred the ball, and it's not going to do much of anything, or maybe not even shred the ball because the torque is so low. So what we want to do is gear that down a bit. So in this situation, we'd probably do like a, I don't know, 1 to 4, something. We probably want like a fourth of that free speed, if not lower. So what's fourth of 18? I don't even know. I can't do math. But we can just go into our pulleys. We want GT2 timing. These HTD timings are for higher torque because like the slots are a lot thicker and they look better in that situation. These are for lower torque. They're a little bit more precise. They're smaller and lighter and easier to work with. And they also don't have the 775. So if we go into our drawing, we want these diameter parts. So these are the, you can see which bore it is, which kind of means like which motor it fits with. So this is the 775 that we want. So we're using the 775. It's going to be 0.591 of the outer diameter. But the inner diameter is what we really want, which is what? The pitch, the bore. So, oh wait, no. We do want the outer diameter. What am I talking about? Because that's what we're counting on here. And we'll make this construction, we'll call it 0.591, which a little bit smaller than the hole. And then on here, we're going to want 1/2 inch hex for time employees. So that one was, this one, the other one that we put in was 12 teeth. So that makes it pretty simple for ratio parts. So let's even just make it like a third, 6,000 RPM. And we don't have to run the motor at full speed, obviously. So yeah, 36 teeth. It's a pretty solid number. 1.535 outer diameter. So we'll CAD that in here. 1.535. It's this one. And then we want to go back on the West Coast products. West Coast products, and then we're going to select the belt calculator, which I've always just searched out because it's a little difficult to find. And this is 3mm, I think. Yeah, 3mm, and you can see right here. Yeah, if you look in the piece, you always find something. This 9mm is a little confusing, but that's not like an option there. So yeah, so it's going to be a 12:36 ratio, and we want this to be about here. So our distance is, it's going to tell me, here to here, 2.626. And you can always find the, if you select two entities on here, it'll always give you like a set of distances. Like if you like select these two circles, then it'll give you like a center distance, and I don't know, sometimes it'll give you like a closest distance. There's a bunch of different stuff you can do, but it's nice that like in SolidWorks you didn't have to, or in SolidWorks you would have to go into like a whole separate thing to check measurements, and it was a whole different process. I don't know, maybe I just didn't know SolidWorks well enough, but let's say our desired center is like 2.5 inches, and then no center add. Okay, 2.6, this is actually not terrible. So that's a 70-tooth belt. And we'll do our center distance here, plug that in. It's a little bit farther than before. Cool. And now we can, decide where to put this. If we want to make this tangent to the edge, we can actually do that. Yeah, that's pretty cool. Okay, so now we have our motor, and it is ratioed to the roller, and we can just kind of mirror it over, and select all this. Oh, that was probably too much to select, but that's fine. And then we have our stuff on both ends. And then we can extrude this. And then let's say we want it to be like an 1/8 inch. And this would usually be like a polycarb or something that we use. And with our, in the past, polycarb has worked out for our intakes, even though it breaks sometimes. But it works better than metal because it doesn't bend, but it can snap sometimes. So, there's ups and downs. But that's pretty much how you would do it. So this is kind of a looser, I guess, I don't know. I think I went through that pretty quickly, and this isn't like the perfect intake or anything, but you pretty much just slap the motor on here, ratio it to a roller, and then it would suck the ball in decently. And you would have like two of these plates and it would be connected. I don't know, it works most of the time. So yeah, and I didn't put in like mounting stuff here either. So I think that's all I'll do today for the CAD. So did you guys have any questions about that or anything at all during about intakes or anything really?
Yeah. I think I'm missing a dimension somewhere, but I'm not exactly sure for the intake.
Okay. Okay. You want
Sure.
me to show the
Yeah.
this sketch? Sure.
Okay, no, I think I'm missing. Were we supposed to make a tangent somewhere?
Um, the motor.
Yeah.
I just put the motor tangent to this, the edge of the thing, just so it's as like as out of the way of the ball as it could be.
Okay.
All right. Is there anything else about design or intakes you guys had questions about, or you wanted me to like review or something, or the CAD even? I think it's good. Okay, cool. Then it's about 7 p.m. So I'll stop our recording and I'll let you guys go.